250, solving the logarithmic equations. Second half of this section.
Are we going to turn on the lights again? Yeah. Light a candle?
All right, if you're going to solve a logarithmic equation, as we have been working through this chapter, every time we hit a log, our strategy was switch it to its exponential form, right? Because we're much more comfortable with exponents than we are logarithms. So if I can take something that is obscure to me and rewrite it in a way that's much more familiar and comfortable to me, absolutely that's what I'm going to do. So we want to switch from logarithmic form to exponential form. So if I had the log base 4 of 8 is equal to 3/2, and we wanted to switch that from its logarithmic form to its exponential form, remember that we had a pattern for switching back and forth between those two forms. To go from logarithmic to exponential, you're going to take your base of 4, raise it to your answer as your exponent, and then what you were taking the log of will become your answer. That was the pattern that we had used. So in essence, I could solve whatever they gave me then. If I switched it to its exponential form, then I'm just back to what I was doing on the first half of this lesson where I was solving exponentials, right? So really they can only leave out the 3 components of the logarithm. Like they could leave out the base of 4, they could leave out what I was taking the log of, 8, or they could leave out the answer, 3/2. So let's go through and let's look at each of those scenarios. Let's look at when they leave out the 4. I mean, we know what the answer is already going to be. We know what this was that we started with. But let's see what happens when they leave out the 4, how we could find that base. When we leave out the answer of 3/2, how we could find that. And when we leave out what we're taking the log of, that 8, how we could find that. Okay? So for the first one, I'm going to switch this to its exponential form. So I'm going to say x to the 3/2 is equal to 8. Now, we've solved this type of equation earlier this year, but it was like back in August. It was forever ago. Anybody remember how we did that? How do we get the 3/2 to go away? Okay, that is x to the 3rd and the square root of that. You're exactly right. So I could undo a square root by squaring, and I could undo a cube by taking the cube root. There's a fast way to do that, like all at one time. All right, what if I raised that to the 2/3? Isn't that squaring and taking the cube root at the same time? Because the idea is I want to be left with just x to the 1st over here. So if I want to clear out that exponent of 3/2, if I'll take 3/2 and I'll raise it to its reciprocal, when you multiply a number times its reciprocal, you just get 1, right? And when I have a power raised to a power, I just get 1. Of course, what I do to one side, I have to do to the other side. So on the other side, I also would want to take my 8 and raise it to the 2/3. And when we have a fraction as an exponent, remember that the numerator is my exponent and the denominator is the index of my radical. So when we had 8 to the 2/3, that's 8 to the 2/3. Now, we get this idea that we have to take 8 to the 2nd first and get 64 and then take the cube root of that. And that's not so bad. But if I have something in here like 8 to the 5th and then I've got to try and take some kind of root of that, that just ends up being a big mess. I don't have to do the exponent first and the radical second. I can evaluate the radical first. Like I can do the cube root of 8 and get 2. And then raise that 2 to the exponent. That's going to be a whole lot easier to work with a smaller value. So like if this had been the cube root of 8 to the 5th, I don't want to figure out 8 to the 5th and then try and find a cube root of that humongous number. Instead, I could do the cube root of 8 is 2 and then just take 2 to the 5th, and that'd be so much easier. So I can go in either order there, and sometimes it'll really help me. So in either case, whether I did 8 squared is 64 and I went the cube root of that, that would give me 4. Or if I did the cube root of 8 is 2 and I squared that, that would give me 4. So again, before we started, we knew the answer that we were trying to get, but we can see how algebraically we could come up with that. All right, what if they left my answer out? Logs into things I think when we could set our bases the same so that we could set our exponents equal to each other, I think that was probably the easiest route, but we definitely could insert an ln on both sides, or we could insert a log base 4. Since I can rewrite 4 and 8 with a common base of 2, I'm going to rewrite this so that my base is the same. So I'll rewrite 4 as 2 squared and rewrite 8 as 2 cubed. And now since my bases are the same, I can set my exponents equal to each other. So if 2x equals 3, then what's x? 3 over 2, right. So again, we knew that was the answer that we were going to get, but we can see algebraically how to come up with that. All right, and then the last type is if they leave out what I'm taking the log of. So I'll switch that to its exponential form. So 4 to the 3 halves is equal to x. And this one is just an issue of simplifying whatever I have on the left-hand side. So if I have 4 to the 3 halves, again, remember that the numerator in a fractional exponent remains your exponent. The denominator is the index of your radical. So that would just be the square root of 4 cubed. And again, you don't have to cube the 4 first and then try and take the square root of that. You can take the square root of 4 first and get your 2 and then cube that. Either way. So those are the 3 components of the logarithm that they could leave out. All right, look at example 6. So example 6, they give me ln x is equal to 2. And if you'll notice, what I'm missing is what I'm taking the log of. So that's basically like this third type that we were just looking at up here. So I'm going to switch it to its exponential form. So I'm going to take its base to the 2 is equal to x. So you might want to rewrite ln as log base e, just so that you can see the base. You don't have to. But then it's easier to see, okay, I'm going to do e to the second is equal to x. If I'm on a portion of a test or a quiz where I don't have a calculator, e squared in and get a decimal and round it to a couple of decimal places. We went from its lesson, we were using logarithmics to undo exponentials, right? So we would insert a log on both sides and it would cancel out the exponential or allow me to undo the exponential. So the opposite of that should also be true, right? If I'm trying to solve a logarithmic equation, I should be able to use an exponential to cancel things out. And so if I insert an exponential with the same base as my logarithm, we have that property of logarithms that says they will undo each other. So since I had ln x is equal to 2, or log base e of x is equal to 2, if I wanted to insert an exponential on each side, I would want to insert the exponential with the same base, that base of e. Now, by definition, when you put in an exponential function is e to the something, right? Or 2 to the something or whatever. That's your base. So when I put that e in on both sides, I put it in as the base that creates an exponent of the equation that I started with. So again, we're reworking the same equation in an alternate way. We said that if you want to undo a logarithm, you could use an exponential. In this particular case, it's a log base e, so I'm using an exponential with a base of e. If I'm using an exponential with a base of e, by definition, that's your base, and the other part would have to be your exponent, right? So when I insert this, I'm going to insert it so that it is down below and that this is my exponent, right? So we have the property that says if you have e to the ln x, that e ln will cancel each other out. So literally, if you put your finger over that, you're left with x equals e squared. That was the answer that we got over here just a second ago, right? You are to your answer literally in just one step. So the e and the ln drop each other out, and you're left with x equals e squared. And then, of course, we could get the decimal for that. So it doesn't matter which way you go there. It's just nice to have some options. Now, when I'm working with logarithms, you might remember earlier in the year when we were solving equations, we ran into something called an extraneous root. And an extraneous root came from, I didn't do anything wrong when I was solving. I solved exactly like I was supposed to, but when I got to the end, I had an extra answer that I wasn't supposed to have. It was an extra root. It wasn't a true solution, and the only way I could find it was by plugging back into the original equation. I run the risk of picking up extraneous roots when I solve logarithmic equations, so I always want to check them. And here's specifically what I'm checking for. Here's where I pick up the extraneous root most often. You cannot take the log of 0 or a negative number, right? So what we have to specifically look for is when I take my answer and plug it back in, is it going to cause me to take the log of 0 or a negative number? Because that's not possible. So that's what I'll have to watch out for. In this case, no problem, because if I take 7.389 and put it right there, I can take the log of that. No trouble at all. All right, so example 8. Yesterday we saw that when we were solving an exponential equation, before we started throwing logarithms into it or anything else, we needed to get that exponential equation alone, right? So that we didn't make a great big mess. Same thing is true with our logarithms. I need that log alone, so what do I need to do first? Divide by 2, right. So let's isolate the logarithm so that it's a whole lot easier to deal with. Simplify that equation down before I start trying to evaluate it. All right. So as we said, to solve our logarithmics, we want to write them in their exponential form. So let's switch this from its logarithmic form to its exponential form. Then how am I going to get x by itself? Divide by 3. So 5 squared, of course, is 25. And we'll divide by 3. So if I take that 25 thirds and I put it back up here, 3 times 25 thirds would just be 25. Yeah, I can take the log of 25. No problem with that. And if I finish checking it, then I would get a true statement there. All right, look at example 9. Example number 9 says solve for x, as we've been doing. Only this time they give me 3 different logarithms. Okay, we just said a second ago that we need to get the logarithm alone on one side by itself. What in the world am I supposed to do when I have 3 of them? How do I get one alone on one side by itself when I have 3 of them? Well, let's see if we can simplify them in any way. Let's start on the left-hand side. Is there any way that you could simplify this left-hand side? You have 2 logs that are being added. Yeah, when I have 2 logs that are being added, remember that I can combine them into one single logarithm that's being multiplied? Let's try that. So I could put the x minus 2 and the 2x minus 3 together. So I could FOIL them, right? It's just a binomial times a binomial. So x times 2x is 2x squared. X times negative 3 is going to give us negative 3x. Negative 2 times 2x is negative 4x. And negative 2 times negative 3 is positive 6. And then we can combine that negative 3x and negative 4x. So I think that's about all the simplifying we can do on the left-hand side. How about the right-hand side? Any properties of logarithms that you recognize on the right-hand side that might enable us to simplify this? Okay. Yeah, we could make that x squared because when you've got a constant out in front of the log, then you can make it an exponent. All right, so now I have the natural log of this quadratic is equal to the natural log of this quadratic. Any ideas from there? Okay, so I heard a couple of really good ideas. All right, we have a property that says if you have the natural log of x equal to the natural log of y, that means that x has to be equal to y, right? It's almost like I'm canceling out the ln. I'm not dividing both sides by ln, but in essence, if we're saying ln equals ln, then whatever I was taking the natural log of has to equal whatever I was taking the natural log of. The other thing I heard was somebody said insert a base of e on both sides, because remember the natural exponential base undoes the natural logarithmic. That'd be a really good way to see how we could, in essence, cancel those ln's on each side. Because if I insert e on each side, the ELN would drop out, and once again, I would just be left with whatever I was taking the log of over here is equal to whatever I was taking the log of over here. So whichever one of those ways you want to think of it, those were all three great suggestions. Okay, so now I have a quadratic I can solve. So how do I solve that? Alright, subtract x squared from both sides. If it won't factor, I'll use quadratic formula, but they were nice enough to give me one that would factor here. What does this factor to? X minus 6 and x minus 1. And so we'll get x equals 6 and x equals 1. And remember that we said that we need to check for extraneous roots, right? So let's take that 1 and plug it back in. And if I put 1 in the place of that x right there, I'm going to get the natural log of 1 minus 2. That's the natural log of a negative 1, right? You can't take the log of a negative number. Same thing happens over here. I would have ln 2 times 1 minus 3, so that'd be ln 2 minus 3. That'd be ln negative 1. I can't do that. So that is an extraneous root. I didn't do anything wrong in coming up with that answer, but it cannot be a solution to this problem. When I plug it back in, it does not work in the equation. So I eliminate it and toss it out. It is not a solution. All right, let's try 6 and make sure that it works. So if I take 6 and plug it in, I'll get ln 4, that's okay. And I'll get ln 12 minus 3, that's okay. And over here, I'll get ln 6, that's okay. I can take the log of each of those values. And then when I simplify those down, I do get a true statement. I do get an equality. So x equals 6 would be my only solution there. I will not list the positive 1. It's not an answer. It's an extraneous root. All right. Then example 10, they teach us the change of base formula, which we have already been using. So they go through a little more explanation and proof of that there. But example 11, they tell us that, you know, legitimately we've looked at all these different ways of solving exponentials and logarithmics, but there honestly are times that it's going to be very difficult, if not impossible, for us to solve an exponential equation or a logarithmic equation by hand, and we would genuinely have to solve it on our calculator. So grab your graphing calculator if you would, and let's look at how we could solve that. So for example number 11, it says approximate the solution of ln x is equal to x squared minus 2. Now, we have solved equations on our calculator probably more times than we can count this year. There were two primary ways that we did that. I'll go back through both of them. It doesn't matter which of the two methods you use, whichever one you like better. But the way that we have done this is we took whatever was in the left-hand side of our equation, so in this case ln x, and we put it in y1, and then whatever was in the right-hand side of our equation, in this case x squared minus 2, and we put that in y2. So left-hand side in y1, right-hand side in y2. I'm looking for where they equal, so what am I looking for on the graph? Intersection, right. Solution equals intersection. It looks like there's going to be two different points of intersection. I did a zoom 6 to start with. I may want to do a zoom 4 just to get a little closer view. Yeah, definitely 2 points. So I can see one of them right here and the other one up here, right? So let's look at how we can find those. Remember, if you want to know the intersection of two equations that you've got in y1 and y2, you can just use your intersect button. So I'm going to choose number 5 down there, intersect. And it will automatically position itself in what I have in y1 and say, do you want me to use this for the first curve? And of course we tell it enter for yes. And then it jumps to what I have in y2. Come on, you can do it. Then it jumps to what I have in y2. I do have an equation in y2, so why does it not want to cooperate? So again, it automatically positions itself on what I have in y1 and says, do you want me to use this for the first curve? And I tell it enter for yes. And All right, so it did position itself on what I had in y1, but it had positioned itself down here off of the curve, so I had an x value, but I didn't have a y value, so that's why it wasn't letting me hit enter. Okay, so now when I hit enter, then it will automatically jump to what I have in y2 and say, do you want me to use this for your second curve? And I can tell it enter for yes. And then it'll ask me to give a guess. Now, I understand that some of us just kind of get in the habit of just hitting enter one more time wherever we are. We don't actually move our cursor to approximate the guess. We just hit enter wherever we were. The only problem with that is when you have more than one point of intersection like we do here, your calculator is going to find the point of intersection closest to where you guess because it figures that's the one that you want. So where I am right now, right here, if I hit enter, it's going to find this point of intersection. If instead I wanted to find this point of intersection up here, I would just have to scroll up here a little bit and hit my guess up there, and then it would alternately find that point of intersection instead. Because otherwise it'll just keep finding that same one point over and over again. Okay. The other way that we did this before was instead of putting the left-hand side in y1 and the right-hand side in y2, we put the whole equation over on one side set equal to 0. So if I move that whole thing over to one side set equal to 0, we would have ln x minus x squared plus 2. And let me turn this other guy off since we don't need him anymore. All right, so now when I graph, remember that solution, root, 0, x-intercept, all synonymous terms. So what I would be looking for here is the x-intercept. And so again, you can see one here and you can see another one over here. And so remember that in our calculate menu, we choose number 2 there. 0, root, solution, intersection, not intersection, I'm sorry, x-intercept, all the same thing. So I would choose my 0, and that's where they're going to ask me to give them boundaries so they know where to look. So we always give them a left boundary and a right boundary and a guess, and then it can find that point. Okay? And we would repeat that process for the other x-intercept as well. So the two ways that we looked at this were we said take the left-hand side of your equation and put it in y1, right-hand side of your equation in y2, and find the intersection. So that's what we did here, where we told it first curve, second curve, and guess, and it found that point of intersection, and then I would just repeat that for the second point of intersection. Or move it all over to one side, set equal to 0, and use your 0 button where you give the left bound, the right bound, and the guess, and you'll notice that's finding that exact same answer. And then again, we would just repeat that for the second point. Okay? So those are skills that we have that we just don't want to lose. Okay? So at this stage of the game, I feel like we have solved like every equation on the face of the earth known to man. Like we have seen polynomial and rational and root, and now we've seen exponential and logarithmic and all of this different type of stuff. And there are a lot of times that I feel like my life is just one great big equation. You can't solve an equation for more than one unknown at a time. Like you can't solve for x and y at the same time if you only have one equation, right? And so the problem with my life anyway is I have like way too many variables or too many unknowns. I can't figure it out. I can't solve it. And, you know, I get really frustrated. How am I supposed to know what I'm supposed to do and where I'm supposed to go and when I'm supposed to do that? And so the great thing is that I don't have to solve that equation. I don't have to figure it out for myself. The nice thing is that I don't have to walk through that equation of life alone. That God knows all the answers, and he's not sitting up there going, I know the answer, but I'm not going to tell you. He wants to give us his very best. And Jeremiah 29:11 says, the Lord speaks.